Hello guys, welcome back to my channel. And in this video I would like to do another Putnam problem which actually brings out the essence of infinite telescoping series. So let's get started, and I'm sure you learn a lot in this video. Okay, so the problem before us is as follows. We have given information that a sub n is equal to the sum from k equals 1 to n minus 1 of sine of 2k minus 1 pi divided by 2n, and all of that is divided by cosine squared of k minus 1 pi over 2n times cosine squared of k pi over 2n, and they're telling us to find the limit as n goes to infinity of a sub n divided by n cubed. So take a moment to look at what we need to find. We need to find the limit as an over n cubed, this ratio, as n goes to infinity. So in order to do that, we, since it's a limit like this of infinite series divided by n cubed, which means they are expecting us to simplify this into some uh, variable in terms of n. It could be a sine, cosine, or anything divided by n cubed, so that you can basically calculate this limit properly. So the first step to solve this problem is to simplify this a sub n expression. So let's do that on a fresh page, and it involves a lot of trigonometric manipulation. So that's gonna require a lot of writing. So let's get started. See you on a fresh page. Okay, so we have a sub n defined this way. I want to just write this in terms of sum from k equals 1 to n minus 1 of sine of k minus 1 pi over 2n plus k pi over 2n divide, because if you add all of them you'll have 2k minus 1 pi over 2n, just like we originally had. I'm just splitting the 2k in terms of k and a k, and the denominator is as it is, cosine squared of k minus 1 pi over 2n times cosine squared of k pi over 2n. And why is this useful? Notice that we are now writing the sine as a sum of one angle and a second angle, and those angles are actually matching with the angles in the denominator. And what's extremely helpful about this is, due to this identity, we have sine of a plus b, which is sine a cosine b plus cosine a sine b. So we can write this compound angle in the numerator in terms of basically two different sum expressions. So we have sum from k equals 1 to n minus 1. First part is sine a cosine b, so sine of the first angle, k minus 1 pi over 2n, and cosine of k pi over 2n divided by cosine squared of k minus 1 pi over 2n times cosine squared of k pi over 2n. That's the first sum, and the second sum is cosine of a. So cosine of this k minus 1 pi over 2n times cosine, we have a sine, right, sine b, so sine of k pi over 2n divided by the same denominator, cosine squared of k minus 1 pi over 2n and cosine squared of k pi over 2n. And one remarkable thing is, you may recognize some cosines are cancelling out, and we can take one cosine from the cosine squared with the sine. So sine over cosine will be a tan divided by a single cosine k minus 1 pi over 2n and a single cosine k pi over 2n, because one of the terms from the square cancels with the numerator. So we have sum from k equals 1 to n minus 1 of, well, one cosine from k minus 1 pi over 2n was used for sine over cosine to make a tan k minus 1 pi over 2n, while a single factor of both of the cosines remained in the denominator. So we have cosine a single of k minus 1 pi over 2n times cosine of k pi over 2n, and a similar thing is happening over here also. So instead of cancelling out the k pi over 2n, we're cancelling out one of the k minus 1 pi over 2n, and then we're using one cosine from the cosine squared of k pi over 2n with the sine to, sine over cosine will make a tangent. So we have a tangent but of a different angle, namely k pi over 2n divided by a single of all these things, cosine of k minus 1 pi over 2n times cosine of k pi over 2n. And noticing both of them have same denominators, we can club these expressions into a single sum to have sum from k equals 1 to n minus 1 of the tangent of k minus 1 pi over 2n plus tan of k pi over 2n divided by cosine of k minus 1 pi over 2n times cosine of k pi over 2n. Now after this simplification, all our simplification based on angles, compound angles, are actually completed. We can't do anything beyond this. Now here is an excellent observation, and this actually arrived to me late when I was actually trying to calculate this sum. One principle of dealing with or simplifying infinite series like this is one principle of simplifying infinite series is to convert it into a telescoping series. And telescoping series again depends on what type of series we have. So if we have an infinite sum, then its telescoping equivalent would look like a difference of consecutive terms. So if we have an expression, say sum of some function f of x, this should be, we should able to write this as, say, f of some x1 minus f of some x2. We could be able to express this in terms of this form in order to convert our infinite sum into a telescoping infinite sum. But to introduce this difference, this negative sign, is actually tricky once we have a sum of tangents in the numerator, right? We have a sum of tangents, we can't change the fact, we can't just throw away the positive sign and make it a negative sign. But given that we have a positive, a sum of tangents, still how can we introduce a negative? For this, I beg you to look at the difference of square identity. A squared minus b squared can be expressed as a plus b and a minus b. So what I'm saying here is, so once you look at this difference of square identity, it may be clear that although we can't have a regular sum of like normal terms, we can make do with a sum with a difference of consecutive square terms like this. So given we already have tan of some angle plus tan of another angle, it's like we have this term, we need to multiply and divide by this term so that we can express the numerator in terms of tan squared of first angle minus tan squared second angle, which in turn has a great chance of transforming into a telescoping series. And the telescoping series is excellent to simplify stuff. So let's go ahead and do that. So as I just explained, we have a a plus b factor. We just need to multiply and divide. Let me use square brackets for change. Let me multiply and divide by this separate factor of tan of first angle k minus 1. um, Rather, let's do it this way. Let's have the greater angle minus the lesser angle, so that we don't end up with a negative. So k pi over 2n minus tan of k minus 1 pi over 2n. And since we need to maintain equality, this tan of k pi over 2n minus tan of k minus 1 pi over 2n term wasn't there originally in our expression. We also need to divide by it, so it's essentially like multiplying by 1, because this ratio will go to 1, minus tan of k minus 1 pi over 2n. And as I said, we can use the difference of squares identity on the numerator. So we have sum from k equals 1 to n minus 1 of tan squared of k pi over 2n minus tan squared of k minus 1 pi over 2n, all divided by now. Let's express this tan in terms of sines and sine divided by cosine, because we have a cosine, so there is a slight chance that some stuff might still cancel out. So we have cosine of k minus 1 pi over 2n multiplied with cosine of k pi over 2n, and this tangent can be written as sine of k pi over 2n divided by cosine of k pi over 2n minus sine of k minus 1 pi over 2n. And believe me, it's a lot to write, the angles are complicated. Cosine of k minus 1 pi over 2n, and all of this is still inside this weird square bracket that we developed. So numerator stays as it is, otherwise we lose the essence of converting this into a telescoping series. So tan squared k pi over 2n, and let's hope that the denominator becomes a constant, otherwise having a variable denominator along with this nice clean telescoping kind of numerator will make it again difficult for us. And again, it's series like these, it's all a matter of chance. You just try everything and you see what best works. Sometimes it may click, sometimes it may not. So it's all up to you to keep doing and trying. And here let's take the LCM for a common denominator. We can have sine of k pi over 2n times cosine of k minus 1 pi over 2n minus sine of k minus 1 pi over 2n times the cosine of, this is the cosine of k pi over 2n, but divided with by a common denominator of cosine of k pi over 2n times the cosine of k minus 1 pi over 2n, and let's close the square bracket. And the best part of today's video, the nasty cosine terms will cancel out to give us sum from k equals 1 to n minus 1 of tan squared of k pi over 2n minus tan squared of k minus 1 pi over 2n divided by, we have sine of k pi over 2n times cosine of k minus 1 pi over 2n minus sine of k minus 1 pi over 2n times cosine of k pi over 2n. And in case at this point you're wondering that we hit a dead end because the denominator is again a function of n, the original of k, sorry, the original indexing variable. But I will say you're wrong if you think we reached a dead end. That's because notice the structure of this denominator. It almost reminds us of this formula. Sine of a minus b is equal to sine a cosine b minus sine a, minus cosine a times sine b. So it's almost like the formula that we used on top. It's actually its counterpart. So we originally used this identity to break apart the numerator. Now we are basically trying to recompose our denominator. So it's inverse functions now. So we have sum from k equals 1 to n minus 1 of this tan squared k pi over 2n minus tan squared of k minus 1 pi over 2n divided by now sine of first angle is k pi over 2n minus k minus 1 pi over 2n. So that's significantly going to reduce the complexity of this sum. So because now we have the sum from k equals 1 to n minus 1 of tan squared k pi over 2n minus tan squared of k minus 1 pi over 2n divided by, you do some simplification over here. Notice the k pi terms are going to cancel out nicely. We just end up with sine of pi over 2n, and the excellent fact is it does not depend on k. So this does not depend on k, which means it can be taken out of the sum quite nicely. So as I said, pulling the sine out, we have 1 over sine of pi over 2n. That is just observing the crazy telescoping sum that we are going to have. Spoiler alert, oops. Sum from k equals 1 to n minus 1 of tan squared of k pi over 2n minus tan squared of k minus 1 pi over 2n, and let's just bracket this out. And now, just for perspective, I'm going to write some terms of this telescoping series to actually show you that this is indeed a telescoping series, and our original logic of writing consecutive terms k and k minus 1 are definitely consecutive terms as differences. In this case, even difference of squares of consecutive terms works out brilliantly to give us a telescoping series. So our entire train of thought was indeed right. You'll be quite satisfied after I show you that. So as I said, just forget the sine part associated with this series. Let's look at just the series now, and let's write out few terms of this. So when k equals 1, we have a tan squared of pi over 2n, and simultaneously minus tan squared of 1 minus 1 is 0 pi over 2n. Okay, that's, you can say, one group of it, and I'm grouping with square brackets. Plus, then when k is 2, we have tan squared of 2 pi over 2n minus tan squared of just pi over 2n. And this can go on until the last terms. So the last terms we have when k equals n minus 1 is tan squared of n minus 1 pi over 2n minus tan squared of n minus 2 pi over 2n. So that those are basically the last terms, and we basically need to don't even need to take the limit as n goes to infinity, because it's not even an infinite sum. So just writing out till n terms, treating it like a finite series, because there was no infinity originally. Anyways, notice that this term is cancelling out with this term. Uh, this term will cancel out with a term that's going to be afterwards, and this term will cancel out with the previous term, because notice how the pattern is going. A positive term will get cancelled by a negative term in the future, by a future negative term, or the next negative term in a forward, in a iteration that's for a greater k, by a future negative term. And vice versa, a negative term is cancelled by a past positive term. So using extrapolating this, a positive term, this positive term got cancelled by a future negative version of this, which was basically negative tan squared pi over 2n. And this negative term, this negative term of tan squared pi over 2n got cancelled with this previous positive term. Same thing applied for this last term, which was negative, got cancelled with a positive term that was basically in the penultimate iteration of this sum. And since this negative term can't get cancelled by any term in the past, because we're starting with k equals 1, we can't start with k equals negative 1. So this term remains, this negative term remains, and this positive term remains because it can't get cancelled by any term in the future, because at n minus k equals n minus 1, this entire sum is ending. So we can't have any more future terms after this. So we essentially have this entire sum just becomes these two terms, tan squared of n minus 1 pi over 2n minus tan squared of 0 pi over 2n will just be a 0. Tan of 0 is 0, square of 0 is 0, so this term goes to 0. The entire sum just becomes tan squared of n minus 1 pi over 2n. And let's substitute this back into our original expression. So now, since we know what this is, our a sub n can simply be expressed as whatever this thing was, tan squared n minus 1 pi over 2n divided by this constant sine term we had, sine pi over 2n, and that's a sub n. And now let's actually find out what the limit is, because remember we had to find limit as n goes to infinity of a sub n divided by n cubed. We know what a sub n is. Let's just write it as a fraction and find the limit. Okay, so we need to find this, that's our goal. Now let's make appropriate substitution for a sub n. So limit as n goes to infinity of tan squared of n minus 1 pi over 2n divided by sine of pi over 2n times this n cubed, which is also in the denominator now in the limit. One thing we can do is we can write this as limit as n goes to infinity. You can just simplify the innards of the tan squared a bit. With n pi over 2n, n's will cancel out with pi over 2 minus pi over 2n divided by the denominator as it is sine of pi over 2n times n cubed. And one nice complementary angle property of trigonometric function was, see, if tan of pi over 2 minus theta, this is just the cotangent of theta, and this applies even for square angle. You can square both sides and you can see that tan squared pi minus pi over 2 minus theta is equal to cotangent squared of that angle. So we can write everything as limit as n goes to infinity of now cotangent squared of pi over 2n divided by sine of pi over 2n and n cubed. Notice we have 1 over n in all the arguments, so I would really appreciate making a substitution. So I would let u equals 1 over n. But we also need to take into consideration what happens as n goes to infinity, right? Because we have a limit to uh, also change when we make this substitution. So as n goes to infinity, u will go to 0, right? Because this fraction denominator will become really, really large. The entire fraction will go to 0. So this entire limit can be written as limit as u goes to 0 of cotangent squared of pi over 2 u, 1 over n is u, divided by sine of pi over 2 u and 1 over u cubed. N is 1 over u, that's why. Now I want to write this as limit as u goes to 0 of cotangent squared of pi over 2 u divided by uh, sine of pi over 2 u divided by u times 1 over u squared. So I'm just taking a u out of the u cubed. And now what I'm going to do is I'm going to multiply and divide by pi over 2 in this denominator basically. That's because notice this part that I'm boxing, this looks familiar, right? Remember this limit as say h goes to 0 of sine of h over h becomes 1. That's the same thing going on over there. So whatever the angle was, say that angle was 4h, for example, we need to match the angle in the denominator, have a 4h in the limit as h goes to 0, then only we'll have 1. We can't have sine of 4h over h in the limit as h goes to 0 being equal to 1. We need to match the angle and the denominator. That's why I multiplied and divided by pi over 2u, so that we match the angle. So by this property, this very nice property of trigonometric limits, this will become 1. So this just simplifies to now limit as u goes to 0. I can write the cotangent squared in terms of cosine squared of pi over 2u divided by, we have a pi over 2, the 2 will go on top giving us 2 over pi basically. And cosine squared, cotangent is cosine squared divided by sine squared pi over 2u. Alongside it we have a 1 over u squared term over here. So I'm going to do same thing like I did with this sign. I'm going to take actually let's take the entire u squared. Let's not take 1u, let's take the entire u squared. Okay, so let's write this as 2 over pi times the limit as u goes to 0 of cosine squared of pi over 2u divided by sine of pi over 2u divided by, let's multiply and divide by pi over 2u, pi over 2 actually, in a square. I'm taking basically the square on both these things because we had a sine squared and a u squared, but we introduced this factor of pi over 2 squared, so we also need to multiply that in the numerator. So pi squared over 2 squared, which is 4. And again, using the property that the limit as h goes to 0 of sine of h over h goes to 1, you can also extend this. If we have sine squared over h squared goes to 1 squared, which is 1. So again, this thing goes to 1, matching the argument and the denominator. This thing goes to 1, and we have 4 goes on top. 4 times 2, 8 over pi squared times pi cubed. The limit as u goes to 0 of cosine squared of pi over 2u. Now this cosine is very easy to deal with when we have a 0, because we have 8 over pi cubed times cosine of 0 times pi over 2 is 0. Cosine of 0 is proudly 1. So this entire thing that we needed to find was 8 over pi cubed, or 2 over pi the whole thing cubed. Isn't that an exciting answer, given the pi's and the cubes and the entire process of dealing with the infinite series, actually not even infinite but series that we had, and making it in a telescoping series and stuff like that. So basically, just to conclude this limit was basically 8 over pi cubed, and hence we solved the problem, the Putnam problem. That's it for this video then. So please like, share, and subscribe to my channel, guys. Recommend me to your friends. I need more subscribers. It seems some subscribers have dropped considerably in the past 4 or 5 days. So I really need to boost, because remember, if I get 100 subscribers, I'm going to make a special question and answer video for you guys. So anyways, stay home, stay safe, and peace out.